in this example, with this information, we have to find the maximum likelihood estimate for theta. Okay. Now, to find the estimate, we have likelihood of theta is the product to n of I is equal to 1 of theta to the power of k, 1 minus theta to the power of 1 minus k. And this theta to the power of k and this theta to the power of k, 1 minus theta to the power of 1 minus k, their product is going to be theta at k1, 1 minus theta also at k1, multiplied by theta at k2, 1 minus theta at 1 minus k2, up to theta at kn, 1 minus theta at 1 minus kn. So, considering theta, we have them here, the same base, which is theta. By loss of logarithms, you are to add the powers k1 plus k2 plus kn. To kn is summation to n of I is equal to 1 of ki. Similarly, we have 1 minus theta here and everywhere. So they serve as the base. We have 1 minus theta. Now we have to add the powers. 1 plus 1 plus 1 up to n times is going to be n. Then here we have minus k1 minus k2, or we can say k1 plus k2 plus up to kn is just summation to n of I is equal to 1 of ki. This is our likelihood function. And to find the estimate, we differentiate our likelihood function and equate to 0. But in doing so, let us simplify this function by taking the ln of both sides. So we have ln of likelihood function is equal to ln of summation to n of I is equal to 1 of ki and 1 minus theta n minus summation to n of I is equal to 1 of ki. So we are going to have ln of likelihood function, their product here, we take them as sum. So we are going to have ln of theta to the power of summation of n is equal to I of ki plus ln of 1 minus theta n minus summation to n of I is equal to 1 of ki. And simplifying this, the power will come down. We have theta. If the power comes down, we have summation to n of I is equal to 1 of ki, then ln theta plus. When this power comes down here, we have n minus summation to n of I is equal to 1 of ki, ln of 1 minus theta. So our function is ln of likelihood of theta is ln of, or we can have summation to n of I is equal to 1 of ki ln of theta plus, here we have n minus summation to n of I is equal to 1 of ki ln of 1 minus theta. Now, to find the estimate, we differentiate ln of likelihood function and equate to 0. That is, derivatives with respect to theta of ln of likelihood function and is equal to 0. It will give us the estimate value. So in differentiating this, summation to n of I is equal to 1 of ki is constant. Then differentiate ln theta, that will give us 1 over theta. On this side, we will have plus, then we have n minus summation to n of I is equal to 1 of ki. Derivatives of ln of 1 minus theta is going to be 1 over 1 minus theta multiplied by derivatives of what is in the bracket. Derivatives of 1 is 0. Derivatives of minus theta is minus 1. So, going by this, we will have summation to n of I is equal to 1 of ki, 1 over theta. Here, we'll make this place to be minus. Then we have n minus summation to n of I is equal to 1 of ki all over 1 minus theta is equal to 0. Rearrange this. We will have summation to n of I is equal to 1 of ki 1 over theta is equal to n minus summation to n of I is equal to 1 of ki all over 1 minus theta. Minus summation to n of I is equal to 1 of ki into brackets theta is equal to summation to n of I is equal to 1 of ki into bracket 1 minus theta. We have just cross multiply. So here we are going to have n theta by opening the bracket minus theta summation to n of I is equal to 1 of ki is equal to summation to n of I is equal to 1 of ki minus theta summation to n of I is equal to 1 of ki. Simplifying further, this will cancel this. So we have n theta is equal to summation to n of I is equal to 1 of ki, and our theta estimate now will be 1 over n summation to n of I is equal to 1 of ki by dividing both sides by n. So, substituting the information given to us, we have theta estimate is 1 over 5, and taking the sum of the ki's, we will have 8. So theta estimate is 8 over 5. Okay, in this example, we are going to calculate the maximum likelihood estimate for lambda with the given information. Maximum likelihood estimate for lambda, we begin by finding the likelihood function for lambda, and is defined as the product to n of I is equal to 1 of the PDF, lambda exponential of minus lambda y. And this is lambda exponential of minus lambda y1 at point 1 times lambda exponential of minus lambda y2 at point 2 times up to lambda exponential of minus lambda yn at point n. Simplifying this, lambda multiplied by lambda multiplied by lambda by loss of indices is lambda to the power of n. Exponential is common, so it's the base. On the power, minus lambda is common, factorize it. Then we have y1 plus y2 up to yn, so we have a summation to n of I is equal to 1 of yi. This is our likelihood function. To ease our work, let's take the natural logarithm of both sides. So ln of likelihood function is ln of lambda to the power of n exponential of minus lambda summation to n of I is equal to 1 of yi. Trying further here, simplify this. Ln of likelihood function of lambda, they are in products. Let's take them as a sum. So it's going to be ln of lambda to the power of n plus ln of exponential of minus lambda summation to n of I is equal to 1 of yi. We can simplify this side. Power can multiply the function. We have n ln of lambda. Ln and exponential neutralizes each other. So we have minus lambda summation to n of I is equal to 1 of yi. This is our ln of likelihood function of lambda. So to find the maximum likelihood estimator, we will differentiate both sides with respect to lambda and equate it to 0. So in this case, here we are going to have n. Ln of lambda is 1 over lambda. We have our minus. Differentiate this with respect to lambda. Lambda will vanish. So we have summation to n of I is equal to 1 of yi and is equal to 0. Simplify further, we have n all over lambda is equal to summation to n of I is equal to 1 of yi. So finally, the lambda estimate is n all over summation to n is equal to 1 of yi. And by substituting this value, the lambda estimate is going to be, our n is 4. Then we have the sum of this, 8.2 plus 9.1 plus 10.6 plus 4.9. We have lambda estimate is equal to 4 over. Okay. Now in this example, with the given information here, to find the maximum likelihood estimator, we begin by finding the likelihood function of theta. So it's going to be the product evaluated at different nkis of theta to the power of 2k exponential of minus theta square all over k factorial. So at the first point, you are going to have theta to the power of 2k exponential of minus theta square all over k1 factorial. At the second point, it's going to be theta to the power of 2k2 exponential of minus theta square all over k2 factorial dash 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 up to a place of n, which is theta to the power of 2kn exponential of minus theta square all over kn factorial. So to simplify this, theta to the power of 2k1 to the power of 2k2 here to the power of 2kn. So theta is the base, right? So we have 2k1 plus 2k2 plus 2kn. So 2 is common. Then we have summation to n of I is equal to 1 of ki. In this one, exponential to the power of minus theta square, the same thing. So exponential is their base. Minus theta square, minus theta square, minus theta square. There is n of them. There are n of them. So minus n theta square all over k1 factorial times k2 factorial up to n value is product of I is equal to 1 of ki factorials. This is our likelihood function for theta. So this is our likelihood function. Let's take natural logarithm of both sides in order to simplify our work. So ln of likelihood function is going to be ln of theta to the power of 2 summation to n of I is equal to 1 of ki plus, because they are product here. So we have ln of exponential of minus n theta square, and for this division we'll have minus ln of product to n of I is equal to 1 of ki factorial. To find the estimate, we will differentiate this function and equate to 0. That is, derivatives with respect to theta of ln of likelihood of theta is equal to 0. So meanwhile, this function can be written as ln of likelihood of theta is the power can now multiply the function 2 summation to n of I is equal to 1 of ki ln of theta. This one ln neutralizes the theta, so we have minus n theta square. Then we have minus ln of the product to n of I is equal to 1 of ki factorial. So differentiating this and equate to 0, here we are going to have 2 summation to n of I is equal to 1 of ki is a constant. Derivatives of ln theta is 1 over theta. Differentiate this, power will now multiply the function 2n theta, power reduced by 1, so you have theta, and this is a constant. The derivative is 0, and we equate them all to 0. To simplify this, we have 2 summation to n of I is equal to 1 of ki all over theta. Taking this to the other side of the equation, we have 2n theta. So we can simplify this by cross multiplication. We have 2 summation to n of I is equal to 1 of ki is now 2n theta square. So our theta square is going to be 2 summation to n of I is equal to 1 of ki all over 2n by dividing both sides by 2n. And finally, we will have theta square is summation to n of I is equal to 1 of ki all over n. Taking the square root of both sides, we'll have theta estimate is equal to square root of summation to n of I is equal to 1 of ki all over n. So this is our theta estimate. In this example, with the given information, we have to calculate the maximum likelihood estimate for theta. So as usual, we will begin by finding the likelihood function of the theta. And by definition, likelihood of theta is given as the product of the function evaluated at different intervals. So we're going to have the product of the function y cubed exponential of minus y over theta all over 6 theta to the power of 4. And this is the same thing as, at the first point we have y1 to the power of 3 exponential of minus y1 over theta all over 6 theta to the power of 4. Multiply by, at second point we have y2 to the power of 3 exponential of minus y2 over theta divided by 6 theta to the power of 4 dash 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 up towards, at point n, yn to the power of 3 exponential of minus yn over theta all over 6 theta to the power of 4. So the likelihood function can be simplified as y1 to the power of 3 multiplied by y2 to the power of 3 and so on is the same thing as yi to the power of 3, and we have their product to n of I is equal to 1. Then exponential is common here, multiplying each other, so it is a base. What do? We add the powers. And in the powers, as you can see, minus 1 over theta is common. We are left with y1 plus y2 plus y3 up to yn. So we have their summation to n of I is equal to 1 of yi all over. We have 6 times 6 times 6 up to n times, so we have 6 to the power of n. Here, theta power 4 multiplied by another, it means it has a base of theta. Then we have 4 plus 4 plus 4 up to n times, we have 4n. This is our likelihood function. Now, we can simplify this complex fraction here by taking the logarithm of both sides. We have ln of likelihood of function is going to be ln of the product to n of I is equal to 1 of yi to the power of 3 exponential minus 1 over theta summation to n of I is equal to 1 of yi all over 6 power n theta to the power of 4n. So by taking the ln, we are going to have ln of likelihood of theta is equal to this product. So we are going to have ln of product to n of I is equal to 1 of yi to the power of 3. Because they are multiplying each other, we are going to have plus ln of exponential of 1 minus theta summation to n of I is equal to 1 of yi. They are now dividing this product. You can have minus ln of 6 to the power of n minus ln of 4 theta to the power of 4n. To the power of 4n. So, to simplify this, we're still going to have ln of likelihood function is going to be ln of product to n of I is equal to 1 of yi cube. Ln here will neutralize the exponential. So we are going to have only minus 1 over theta summation to n of I is equal to 1 of yi. Then minus n ln 6. Then minus 4n ln, here we have only theta. Minus 4n ln theta. Now, to find the maximum likelihood estimator, we differentiate both sides with respect to theta and equates to 0. We'll have d theta ln of likelihood function is equal to 0. This is a product, this is a constant, it does not contain theta, so derivative is 0. For this side, we are going to have summation to n of I is equal to 1 of yi. We have our minus here. This 1 over theta here is the same thing as theta to the power of minus 1. So these derivatives, we are going to have minus theta minus 1 minus 1. This is the derivatives of this side. Now, this is a constant. So, derivative is 0. This one, we are going to have minus 4n. Then, differentiate in theta, we are going to have 1 over theta. And it's equal to 0. So, this side now, minus minus here, we are going to have plus. And this is the same thing as theta to the power of minus 2. And the same thing as 1 all over theta square. Then we have summation to n of I is equal to 1 of yi minus 4n over theta is equal to 0. So simplify this as well. So we are going to have 1 over theta square summation to n of I is equal to 1 of yi is equal to 4n over theta. Simplify this. We have summation to n of I is equal to 1 of y1 is equal to 4n theta square all over theta. We multiply through here. So still divide both sides by 4n. We have summation to n of I is equal to 1 of yi all over 4n is equal to theta. So this is the theta estimate. So substituting the values given to us, the summation of yi is this and 4 over n here it is. So if you add this, this is 2, 3, 7, 8.5, 8.8. So 8.8 over 12, something 0.733. So this is our theta estimate.